Next speaker is Scott Zoldi. He is the Chief Analytics Officer at FICO, driving innovation in artificial intelligence with a focus on standards for explainable AI, ethical AI, and responsible AI. While at FICO, Scott has been responsible for authoring over 110 analytic patents, with 71 patents granted and 46 in process. Scott serves on the boards of directors of Tech San Diego and Cyber Center of Excellence. Scott received his PhD degree in theoretical physics from Duke University. Thank you, Scott. Go ahead.
Thank you very much, Cherrill. And thank you to the APS for allowing me to speak today and share a little bit about my journey. The talk will be around combating the blind faith in machine learning, which is a really relevant topic today, and I'll try to motivate that if you're not already of that opinion. My background was provided already, but one of the things I'll do is paint a picture. I was doing my PhD at Duke University in the late 1990s, and I was focused on a topic of chaos theory, right? And chaos theory was very hot at that time, and I would study equations related to Lorentz attractors and fluid dynamics and understanding the transition to turbulence. When I finished my work at Duke University, I went to Los Alamos National Laboratory, where I studied the concept of shadowing theory, which basically states that it's for many types of problems that we try to understand or simulate, it's nearly impossible to do so. So I spent a great deal of my career as a physicist focused on systems that can't be predicted. And I got attracted to, why is the industry around me, the world around me, perfectly fine making predictions, whereas the simplified models that I try to study are so unpredictable. And it led to a journey where I joined a company called FICO. And FICO interested me because it had most of the world's data, particularly financial data. And so the resources I had at a company such as FICO to explore my research ideas far outweighed that of the national labs at the time or universities. Today, FICO is a relevant company. You may know of us, right, if you've looked at your FICO score for credit lending. If you use your credit card, 9 times out of 10 is one of our models that have made a determination whether or not there is suspected fraud on your account. But it's a company that was founded more than 50 years ago, and it was really the first company to focus on using mathematics and empirical models to fairly extend credit to individuals. So you no longer have to walk into a bank and determine whether or not the banker liked you, or whether you went to the same country club or to the same church, or you were the same color or creed. It was based on empirical data, and that's been the formation for my company. And a big source of inspiration for me personally. Now, when I joined, machine learning was already well underway. In the late 90s, most of the banks are already using machine learning models, in particular neural network models, for all kinds of scoring of financial systems. So they would collect all your data. They would know whether or not, based on your transaction history, this current transaction is similar to what you would be expected to do or not. If not, they would flag it as potential fraud. And at that time, people were very skeptical of machine learning, right? It's very different than today. Today, if I put machine learning in your cereal, you'd gladly eat it, because we've been accustomed now to the fact that machine learning can solve all problems. And we've become comfortable with giving up every slice of data associated with our lives and having all our information tracked, which causes a huge sort of challenge around the responsible use of that data and responsible use of decisions derived from that data. We're faced with this sort of focus that the entire industry and our lives from this point forward will be driven by machine learning and AI models, primarily because the data that we generate is so valuable and it drives so much of what we do. And machine learning and AI is powerful because it's superhuman, right? And I'll reflect on a little bit in this talk around my own humbling experiences trying to understand simple equations and knowing that I would never have an ability to do so, right? Whereas a machine and an algorithm has an ability to pull out incredible insight in relationships and data that a human being couldn't. But I want to come up with two definitions, because these terms get used interchangeably, and it's really important to understand the differences. AI, machine learning, is considered superhuman. Right? Artificial intelligence, as a broad definition, is any technology that performs cognitive tasks at a superhuman level. It's typically technology that a human being has instructed to get at information, data, and generate an output. So as an example, like if you wanted to go to the airport, you put in your Google Maps, it's going to access information about the maps, it's going to get real-time traffic, it's going to calculate a whole bunch of different routes, it's going to present you a route, and you're going to happily get to the airport within a couple of minutes of what that estimate is typically, right? Or if not, it will reroute you in real time. Now, there's no machine learning there. That's just access to data and a programmer telling the algorithm what to do and how to do it. It's completely predictable how it will work as the data changes underneath it. And that's safe because the human being has an ability to control and to monitor what that algorithm does. Where our lives are headed is in the area of machine learning, right? Which is the science of algorithms that learn relationships from data rather than from explicit programming, which essentially means that the human being does not have an ability anymore to prescribe or write code that would explain what are the relationships and types of data that the algorithm should use. So we have these algorithms that have been developed now where you present it with huge amounts of data and outcomes, right? So the data could be everything related to your credit file, and the outcome could be whether or not you were delinquent on a loan or not. And the machine learning model will happily go and look at all the different combinations of data across the corpus of examples that it has and produce an outcome. Now the challenge is these machine learning models are really complicated typically, and typically not understandable. So although they do a better job than any human being, no one, for many of them, understands how they actually work, which poses a lot of sort of challenges that we'll talk through. But be assured, right, AI is everywhere and it will be everywhere. And we have, we've crossed that chasm. And, if I was giving this talk about 10 years ago, we'd talk about the Terminator. I think there are much more scary things out there than the Terminator, right? And so I want to focus on those, the things that fundamentally impact each of your lives and the lives of your children to come based on AI. Today, here's just a few examples, right? Self-driving cars. In fact, on the plane ride over here, I remember I sat next to a mom and a child, and the child was worried about driving when he grew up, and the mother explained that there'd be no need for him to worry because there'd be no driving cars, and it would be fully automated. And so that put the young boy at ease, right? It doesn't put me at ease at all. But we see AI being used everywhere. Healthcare, human resources, banking, and finance being one of the most mature industries to use it. And all that data that you collect on your apps and your smartphones, right, are all powering AI decisions all the time. But AI, being superhuman, is also dangerous. It's tremendously dangerous, and dangerous in ways that create social inequity, create harmful and potentially deadly consequences for people. For example, racial bias being found in the major healthcare risk algorithms, such that if you don't understand that, you certainly don't want to take a recommendation from there. Compass is an algorithm that makes a decision who's let out for parole, deemed to be fair, but when Political looked at it, it was 2 times more likely to misclassify blacks versus whites in terms of being incorrect, meaning that if you were of black class, you were, as a class, being discriminated against. And then Amazon, which should know better, right? They have, more AI and machine learning and resources than anyone in the world, creates an algorithms to hire people and finds out that it's severely biased towards women, primarily because they didn't think about the data they put into the algorithm. They asked for hobbies and things like this, and that imputed gender and race and other things that caused a systematic-wide sort of hiring, misclassification, and bias. So these things don't pop out. They come out years afterwards when you look at the data and ask the question, why are there so much disparity here? Now, fortunately for us, right, regulation and social awareness is out there, right? The GDPR is a set of regulation out of Europe, which focuses on the proper use of consumer data. The IEEE standard basically is out there that now focuses, it was published in 21, that says that you should always be able to explain a model and not allow models to be unexplainable. We have advocacy groups that are protesting and trying to educate people about the fact that they are being, the outcomes are determined by an algorithm. And we have books out there, such as The Weapons of Math Destruction, if you haven't read it, right, around how these algorithms systematically can, built incorrectly, impute bias. So it's a big, scary problem, and it's one that I worry about quite often. So why does this happen? Well, you know, we all heard of Moore's Law, right? I think Moore's Law could also be more wrong in terms of more cloud, more open source creates hugely complex models. And sometimes it's a bravado thing where each scientist wants to prove that they can build a bigger model and consume more electricity and harm the environment more with a carbon footprint than actually building a model that is appropriate. Right? And the models then that end up ruling us, and I'll use the word ruling us, right, are often not understandable. Now, for a physicist, this is completely unappealing. And it's one of the reasons why I've been at this job for 23 years, and I'll probably be at this job for another 23 years, because there's so much work to be done here. So let me give a perspective of where I was as a physicist. So, you know, I was at Duke University. I was funded by the DOE. I had a computational science graduate fellowship, later on doing continued work at Los Alamos as a director fellow. And I was intrigued by the Lorentz attractor, right? So for those of you that are unfamiliar with chaos, right, it's a very simple differential equation. It's not a partial differential equation. It's a simple differential equation. And the way chaos works is that an infinitesimal amount of noise on a trajectory in some finite amount of time will lead to a completely different outcome, like fundamentally different outcome. And it doesn't matter how hard you try to better simulate the equation, because that infinitesimal amount of noise will cause you to move around this chaotic attractor in a way that you cannot predict. And at the time, right, you know, I was pretty humbled by this. And one of the things that I decided to do was to say, well, you know, I need to really understand the dynamics of these systems. And so I started to create analytic equations and numerical simulations calculating unstable periodic orbits. And so what you can do for these chaotic systems is understand that when they are in a state of being chaotic, there are a infinite, probably, set of unstable periodic orbits that define the manifold on which this dynamics operates. And so you're essentially moving on one of these unstable periodic orbits to another one, and you're bouncing around. And so by extracting all these unstable periodic orbits, I can explain the dynamics of this entire chaotic attractor, right? Which basically means that if I can fundamentally understand the objects or the latent features that describe the dynamics of this chaotic attractor, now it's not as concerning to me because I can understand essentially what the escape rate is associated with one of these unstable periodic orbits. I will have some level of periodicity because I'll know that I'm within a vicinity of a periodic orbit. I can make better predictions. So even something as simple as a very simple differential equation being unpredictable led me into these sort of focus on these latent features. Now, pivoting to machine learning. This is a neural network. A neural network essentially is an equation. And the way it works is that you have data on which you allow the algorithm to learn the relationships it thinks it needs to find to maximize the prediction. So here we have six different variables related to credit risk. We have this hidden layer, which is basically nonlinear functions of those 6 inputs. And these are things that activate, right? So when they find a relationship that matters to the target that we're trying to predict, let's say whether somebody is written off or not for delinquency, they'll fire and cause a score to be high or low, meaning that you have a high level likelihood of defaulting or a low level of defaulting. And the only optimization constraint that's used, and probably for most cases, even today, is simply an optimization constraint which says that the output of this neural network should be close to the answer. And you just keep trying, and you use something which is called a gradient descent algorithm, which adjusts all those little green knobs there, right? There's essentially 21 weights to this equation until you maximize your ability to make a prediction or minimize that cost function of making mistakes. And that is how most machine learning is trained today. It's simply to, at all costs, to go and to come up with the best prediction. Now the challenge is that these models are really hard to explain, and this one shouldn't be so hard to explain because it fits on one slide, but it is because they leverage a nonlinear function here, a tan h is typical, and when you use this tan h, you essentially are saturating the features that are identifying the highest sort of contributors, new features, right, that you may not know. And there could be many different ones that activate this latent feature 1, which causes the tan h to saturate positively or negatively. But to go and say concretely to someone who just got declined a loan that they rely upon for their livelihood and will impact or set them back in their life, potentially their entire life, you need to have more certainty than a set of guesses around what might be the reason, because people want to remediate that, right? It could be a data issue, it could be a lifestyle issue, it could be something that they could work towards, right? That level of transparency doesn't exist even in this simple equation. So the question is then, well, if this simple neural network can't be explained, right, what about the more complicated ones? Now, one of the things that are really a big challenge today is that as we build models that are high level of prediction, we find out that we could have bias. And this is something that's in the credit risk environment is called disparate impact. I'm actually on a number of advisory panels associated with responsible credit lending. And disparate impact basically means that one class of individuals will have a very different outcome than a different class of individuals. Now, the purple versus the orange classes here, their color is not fed to the algorithm, but there's lots of things about the data that could have correlations that impute race or gender or creed or nationality or other things that would cause a disparate impact. And so typically what ends up happening is that people can measure this after they've leveraged these models for some period of time and created this disparate impact, but they don't know how to fix it. Right? So we have to do something different. In fact, we have to basically say that it's unacceptable, and we have to look at the internals of these models and understand the latent features, right, or the fundamental behaviors, much like the chaotic attractor, which is unexplainable until you start to look at the basis of unstable periodic orbits that define its manifolds. We have to come up with new types of algorithms. So we invented a constraint here, right? We basically said, well, maybe we should create and enforce a policy which says that we need these things to be explainable. Yes, we want it to be predictive, but now we're going to change the constraint. So if you look at that constraint in the upper right-hand side, we have the difference between the answer, which is A, right, default or not default, and the prediction Y, which comes out of this neural network. And you have another term, which is a summation of weights. This is a regularization term. And what it basically does is minimize the number of weights in the neural network. And in fact, right, if we suspect one of the nodes, so for example, if I go back one, I suspect that maybe latent feature number 3 is driving disparate impact, I can go and apply that Highlander constraint where I can basically specify that there could be only 1 or 2 connections to any latent feature in this new neural network. So I'm creating another neural network to explain one of the nodes, and I keep decomposing into smaller and smaller levels. Now, the importance of this is now I can say very succinctly, right? For example, latent feature 33 is a nonlinear relationship between the number of collection events greater than $500 and a total mortgage balance. So when somebody gets that latent feature activated, we're going to have a conversation and say, well, you have a very large mortgage amount that you're trying to get a loan for, but you have a lot of collection events. And so that is something that has to be addressed, right? Or understood by those that are granting credit. Beyond that, if we just use the regular neural network, that level of transparency wouldn't be there. So we can explain every relationship, and it's important because some of that regulation I showed you earlier basically says that a human being has to speak to another human being to tell them specifically what it is that caused the machine learning model to come up with the decision. It can't just be that the science told me so, right, or the cloud computing outcome did. And so this level of transparency is incredibly important, and we call it interpretable models. The second part of this is that once we start to have that level of transparency, right, we can examine each of the simpler relationships, ones that you could explain to your boss, to your friend, to your neighbor, to your child, in terms of what might be driving a bad outcome for you. And then look at our two classes of purple and orange and understand what is responsible for the disparate impact. And so by doing this, then we can start to decompose the problem into the features that matter for prediction. Some are acceptable from a disparate impact perspective, meaning that there's no difference between our purple and orange groups. And some that, although good for prediction, right, are bad for a particular protected class of individuals. And actually, by doing that, then you can impose constraints when you train these models to never use those relationships. It goes back to what was said about the IEEE standard, which is essentially the fact that you need to have as simple of a model to achieve a task and one that is understandable and not biased. So this focus on the core sort of contributors to the dynamics is really, really important. And it's a key part of what I, as a physicist, has always focused on, is to really decompose these problems. And so now there's new science, right? This new science is around models that are going to be used for things that are critical. The EU released some regulation last year, and they defined different types of AI and machine learning as high risk, right? So high risk includes things like video surveillance, right? Policing, and credit risk, right? And you wouldn't necessarily put credit risk in the same category until you realize, obviously, that if you don't get your loan or if you get it for many percentage points higher, right, it does have a very fundamental human impact, particularly if it's disparate, right? So, one of the main drivers for me as a physicist has been this sort of focus on not taking for granted the fact that because I can build a complicated model and I can use a whole bunch of cloud computing and I can show that I have a great performance, that's in any way acceptable. Now, this is still a challenge because most of the industry, including our financial industries, don't quite recognize this yet, right? We're still grappling with this sort of attractiveness of prediction at all costs without protecting those that could be impacted by it. But this is really a big focus, and it's around this fundamental belief that I have, right, that we have to, as physicists, really focus on what drives that dynamics. Now, for the last little bit of the talk, I want to talk a little bit more about that, because today, right, many models aren't built by mathematicians or physicists or people that actually understand the mathematics or statistics, right? The amount of mistakes that a physicist or a mathematician or statistician that would turn their nose up to as just fundamentally flawed from day one are amazing. In fact, Citibank, right, they've as many as 90 to 95% of all models get rejected, right, because of just fundamental math mistakes and physics mistakes. And so this is complicated, right? And so because it's complicated, the other portion of being responsible here from a societal perspective is to make sure that we don't leave these models that impact all of our lives to a data scientist's artistry. We need blueprints. As such, right, we're proposing many different sort of things that drive governance standards. And so this is really around a codified corporate model development process, which includes things like lists of requirements and development sprints and the specific resources that are assigned to it, the assumptions, the success criteria, the data and whether or not it's biased or sampled correctly, explainability, bias detection, approvals, the whole bit. So it's a whole process where if I go onto Amazon tonight, I can build you a model in about 2 hours. If I build a model with a process like this, it takes me 3 to 4 months. But when I build that model that takes 3 to 4 months, it can work for 3 to 4 years. And we know exactly what it's going to do as environments change. And frankly, right, our entire lives and our environments are changing, right? We are still in the middle of a COVID pandemic, right? We see dramatic changes in customer behaviors. We see, even today, right, gas prices rising, the conflict in the Ukraine. We have lots and lots of change. And all these things impact these sort of models, right? So it has to be persisted to a blockchain because we need permanence to what was used in the development process. Now, that enforces that a modeling process is followed. Now, the modeling process may not be perfect, and that's okay. We can iterate and make it better over time, but it has to be done consistently across teams. I have about 150 data scientists that are building models. I can't have 150 different ways or preferences. And it has to be on the blockchain. And many people will say, well, why is it on the blockchain, right? And the reason I put it on the blockchain is it has to be immutable, meaning that there should not be a situation where somebody can change the fact of what was done and how it was done. Right? There's an interesting statistic of something that I pay attention to that about 2/3 of your colleagues routinely lie to you, right? And so you need to enforce that these sort of decisions are so paramount and important that you are willing to sign up for it in the blockchain. And it's okay, I'll make a lot of mistakes, we all make mistakes, but that level of transparency is incredibly important. And when you do that, what you have, and these are pictures of some of the scientists that I work with, right, you actually show the process working. You extract the latent features, such as this latent feature 31, right? You look at the two-variable interaction latent feature. You look at it and say, yeah, we believe that to be reasonable and not in violation of any sort of regulatory concerns. At a later stage, right, we might do bias testing and understand that, well, that same variable is failing on the bias test, right? It was rejected. We had to retrain the model. We redid the compliance testing, and it's approved. So it's a system of record, right? It's not a celebration of a model build. It's actually to show the mistakes and that their due diligence was made and done in development of these sort of models so that we can understand the entire provenance of this model, because it doesn't matter until it's used in production. When it's used in production, we need all these details to understand how the model may shift in production. And so the way this works then is essentially, as you build these models, you know what they looked like at the time you built them, you understand the relationships that drive them, you can explain that to the regulator, to your governance team, to your boss, and to your mother, right? But you need to ensure that they continue to be ethical and responsible in production. And so there is a lot of focus now on machine learning monitoring. And so by monitoring these models, we can't just look at the score and how it looks on the orange and purple populations, right? What we need to do is look at the latent features that are driving these models and how they change over time. And one that might not be biased today could be very biased tomorrow. For example, during COVID, the Hispanic population was disproportionately impacted by COVID based on the type of work that they did. Right? And so these sort of things happen all the time in production, and it's part of how we're going to monitor and ensure that we do not have that blind faith in these machine learning technologies. With that, I just wanted to thank you. I hope the focus on really this core understanding of what drives machine learning models, right, and the core dynamics from my early days in chaos theory to what I do today in terms of financial industry helps with a bridge, right? But also demonstrates that we need more people that ask really good questions about why and how, right? And I don't believe it, and they call bullshit on things, right? Or else we're all going to be in a little bit of a challenge in the future. So keep that in mind as you look towards your own paths. Thank you.
So we have time for one question. Would you come up, please, and say it into the microphone? And those of you online, now is your time to type it in.
Hi, thank you for your talk. This is a topic of great interest for a lot of different fields. I was curious to your thoughts on quantum computing, because as quantum computing becomes more prominent, I would imagine that on one hand, it would have the ability to wreak havoc and create even more complex neural networks due to its power and just ability to do even more computations than our best supercomputers. But also, it may possibly have the ability for us to unravel some of these complexities within there that we can't really explain as humans. So I was just kind of curious as to your thoughts on that.
Thank you, yeah. So it's a great question about quantum computing. My first reaction is typically the quantum computing is used for like a lot of the matrix operations we do in machine learning, and so there's a lot of promise there. But I think primarily when you have to get into the quantum computing realm, you're dealing with really, really large data sets and lots of types of data. And so the complexity of the model comes with that need for the quantum computing. And so one of the things that I had an opportunity to do is to talk to my advisor about a month ago and explain the concept of good enough, right? And good enough basically is, if I can have a simple model that everyone understands, everyone agrees is workable, we may not need all that computational power. So I think although there's lots of great applications for quantum computing, I think for these ones that impact social social issues and inequality, it's probably not going to be the right equation because it will just get more complicated in terms of the quantum states and all that exploration and the fact that we probably don't have legitimate data to actually power the machine anyhow in a real objective way. Thank you.
Any further questions? Please come up and use the mic.
Yeah, thank you very much for the talk. I had a couple questions. So have you thought about using adversarial training to debias your network?
So yeah, so we have. So adversarial training we've used as another sort of constraint. Today, though, unfortunately, it's considered in many environments as itself biased and potentially illegal. So it uses sort of an outcome and it puts it on the data scientist to try to debias by allowing the model to train based on the outcome of one of those classes. So although it's a technique that can be used, from a legal perspective, it's still a challenge whether or not it should be used. So we don't use it specifically when we use the outcome data. We do more of what I showed you there where we look at latent features, because that latent feature doesn't say whether or not you're going to default or not. It simply says how it activates. So that's one way that we're using debiasing, but not specifically, let's say, on an outcome of one class versus another.
Okay, that's interesting. So you're saying in order to use it, you would have to label the data in a certain way that's prohibited. Okay.
Correct. And there's some lawsuits. It was around promotions associated with firemen. And so by the legal precedent, and it was out of a legal team in Stanford that looked at it, basically said that in itself, trying to bias it towards one group or another, even if you're fixing what might be biased data, itself is another form of bias from a legal perspective.
Yeah, that's a really interesting perspective. And I was wondering if you could point us to the white paper of your method.
Yeah. Yeah, absolutely. Yeah, we can make that available. Yeah. So I think the best way to do it is either to hit me on LinkedIn at Scott Zoldi, and I'll just send you the link, or the Scott Zoldi on Twitter. Either one. Thank you.